In this session of Work, Energy and Power, we will discuss the topic Work-Kinetic Energy Theorem and the application based on this theorem. What you have observed, I have applied a force on the mobile, and due to the application of the force, the kinetic energy of the mobile has changed. Initially, the kinetic energy of the mobile is 0 because the mobile is at rest. After the application of force by me, mobile has got some speed, and due to this, the mobile has got some kinetic energy. Right? And hence, using this, we can define a work and kinetic energy theorem which states that the work done will be equal to change in kinetic energy. That means it will be equal to half mv square minus half mu square. Here v is the final speed of the object, u is the initial speed of the object, m is the mass of the object. Remember that this theorem will be applicable only when we have applied a force, and due to the application of force, the work performed will go into only the kinetic energy. We are going to derive the work kinetic energy theorem. The derivation is based on using the Newton's second law. If you apply some force on an object, then according to the Newton's second law, the net external force will be equal to mass into acceleration, right? As we know that the acceleration is given by dv by dt, right? But this acceleration can be written as dv by dx into dx by dt. As we know that this is the basically velocity, hence we can write down it as v dv by dx. That means the acceleration a will be equal to v dv by dx. Hence, using this, we can write down a as v dv by dx. Now we are going to integrate both sides. When the object is at the position x1, then at that moment the speed is u, which can be called as initial speed. When the object is at the final position x2, then the final speed of the object is v. This quantity represents the work performed by the force F. When the force F will act along the displacement of the body, we are taking the mass of the object as constant, hence this constant quantity will come out from the integral. Now v dv will be integrated, and from the integration v dv will come out v square by 2. Now place the lower limit and upper limit. First of all, place the upper limit. That means you have to place the value of v, then you have to place the lower limit. After placing the limit, the expression will come out this one. That means work done by the force F will be equal to m v square by 2 minus u square by 2, and this is the basically change in kinetic energy. We can write down this expression as this one, work done equal to half mv square minus half mu square, and we know that half mv square minus half mu square is the change in kinetic energy. This one is the final kinetic energy, this one is the initial kinetic energy, and this one is the work performed by the force. Hence the work kinetic energy theorem is derived. Now I am going to discuss problem, and I have taken this problem from Fundamental of Physics, Halliday, Resnick and Walker, 5th edition, from the chapter 7, and the problem number is 17. The mass of the object is 3 kg and it's a particle like object. That means we can take the very negligible dimension of this object. This is the meaning of particle like, and the position of the particle is changing with time t according to this relation which is given in the problem, 3.0 t minus 4.0 into t square plus 1.0 into t cube, and x is in meter and t in second. We have to find the work on the object by the force from t equal to 0 to t equal to 4 seconds. Here we have to keep the concept of significant figure in our mind to write down the final answer. Each and every quantity in this problem has two significant figure, and hence our answer of work done must contain two significant figure. Now first of all, what is the concept behind this problem? The work will be given by, once again, final kinetic energy minus initial kinetic energy. Work done will be equal to half m into v square minus half m into u square. Now we have to find the value of v and u. Here the mass is given at 3.0 kg, mass equal to 3.0 kg. Now we have to find the value of v and u. How can you find the value of v and u? Here the position of the particle is given and we have to differentiate. Now to find the value of v, we have to take the differentiation of position x with respect to time t. That means we have to find the value of dx by dt, and the value of dx by dt. 3 is constant quantity, it will come out from the differentiation, and the differentiation of t with respect to t is 1. That's why the differentiation of 3t will be 3. minus 4 will come out. The differentiation of t square will be equal to 2t plus the differentiation of t cube will be 3t square. Hence the speed v is given by 3 minus 8t plus 3t square. This one is the initial speed, because if you put the value of t equal to 0, this one is 0, this one is 0, hence the speed will come out 3 meter per second. Now put the value of t equal to 4 second and you will get the final speed v by putting this value t equal to 4 second, and after some calculation you will get the value of final speed will be equal to 19 meter per second. The value of mass m 3.0 kg, value of v 19 meter per second, value of u 3 meter per second in this equation that we have calculated. Then you can get the value of work performed, and the work will be equal to w will be equal to half 3 kg into 19 square minus half, once again 3 kg and 3 square. After some basic calculation you will get the value of 528 joule for the work done performed by the force F acting on the object, by keeping in mind the concept of significant figure, because the final answer must contain two significant figure. That's why we have rounded off this 528 joule into 530 joule.